speaker of the session is Dr. Rozema, and he is a senior scientist at the University of Vienna, and he will tell us about experiments in quantum foundations, focusing indefinite causal order in quantum mechanics. Dr. Rozema, would you like to check your slides?
Yes. Can you hear me?
Yes, absolutely.
Okay, great. So can you see my screen, my slides?
Yeah, absolutely. And they are in full screen mode.
Okay, great.
We are ready to go. Okay, so the stage is yours, please.
Okay. Let me just try to find. You can see my cursor as well?
Yes, absolutely.
Great, I'll just use the cursor then. Okay, yeah. So yeah, thanks for the opportunity to present that work here. So and thanks for the introduction. So I'm a senior scientist at the University of Vienna, and I work largely in experimental quantum optics and quantum information. And today I'd like to present kind of two lines of work that we've been studying in the past couple of years. The first is on indefinite causal order. And then I'm going to kind of switch gears a little bit and talk about something else, which is how we recently implemented a Maxwell's daemon using thermal states of light. So, okay, yeah. So first off, for the indefinite causal order, I'd like to start by introducing the particular process that we study. So most people in this field, I'm going to take my time and introduce the field so that you know what I mean when I say an indefinite causal order. So I'll get to that in the next couple slides. But what I'd like to start by introducing is one particular process, which is the quantum switch. And then I'll show you how we've been making these sorts of processes in the past. And try to motivate why we've taken a new approach to using active optics to implement these processes. And then I'll show you our very first experimental results where we've used time bins and active optics to implement the quantum switch. And I'll get into some of the details. The paper on that actually just came out this morning on the archive, so it's quite fresh. And then we'll get into the Maxwell's daemon. So I'm going to roughly split my time 50-50 between these two topics, where we'll focus more on, where first I'll discuss an optical analogy to Maxwell's daemon. As we know, Maxwell's daemon doesn't typically use photons, so you have to do a little bit of thinking in order to figure out how to implement these sorts of experiments with photons. So I'll take some time to introduce that. And then I'll show you how we, the details of our experiment and how we actually used entangled or correlated photons to give the daemon more power, so you could extract even more work. Okay, so with that, I'll get into the first topic, which is this idea of an indefinite causal order, and in particular, talking about this one process, the quantum switch. So the quantum switch was originally proposed back in 2013. So yes, I guess about 10 years ago, by Giulio Chirivella and co-authors. And Chirivella is now one of the leading researchers in the field studying these sorts of topics. And he introduced this as a theoretical concept in this paper, which ultimately came out in PRA, Quantum Computations Without a Definite Causal Structure. And this was actually one of the very first things I worked on when I moved to Vienna. So our experiment came out a few years later, where we showed how we could create superpositions of orders of quantum gates. So this is this causally non-separable process that we can actually make in the lab. So now, what do we mean by a causally non-separable process or a superposition of indefinite causal order? Both of these phrases mean essentially the same thing, so I may use them interchangeably. The basic idea is it's a generalization of a quantum circuit. So we're all familiar with the standard model of quantum computation, which is a circuit model. So in the circuit model, we imagine a series of wires, and these wires each contain some quantum state. The quantum states then proceed through the wires in an orderly fashion, and the gates are applied in a predefined order. So before we run our quantum computation, we have a well-defined order in which the gates are applied. And the wires connect these gates and connect the gates in this order. And this is essentially the quantum circuit model. And the quantum circuit model is an incredibly powerful model of computation. It's universal, which means we can implement any unitary operation on these input states. And although there are other models of quantum computation, typically when you try to develop a new model, such as measurement-based quantum computers, in order to show that it's universal, you kind of try to show that it's equivalent to the quantum circuit model. But it turns out the quantum circuit model isn't given by the laws of physics. This is an extremely powerful technique, but it's something that is somewhat arbitrary. We've chosen it because it's easy because you can show that you can achieve universal quantum computation using it. But we can do other things beyond the quantum circuit model. So we can imagine an extremely simple scenario. So let's say we have two unitary gates, single qubit gates. We'll call them U1 and U2. Now we can send a quantum state through these gates by simply taking a wire and connecting the two gates with the wire. In this case, the quantum state is going to proceed through the wire. It's first going to see U1, and then it's going to see U2. We could also choose to do this the other way. We could also connect the wire so that the quantum state is first going to go to U2 and then to U1. And if you're working within the quantum circuit model and you have these gates U1 and U2, this is essentially all you can do. Of course, you can vary the input state, but the only real ways you can connect these two gates are the ones I've shown you. But quantum mechanics would also allow us to do something a little bit more exotic. We can also take these wires and put these wires in a superposition. So now we have, and if we do this and we send our quantum state into these wires in a superposition of the black wire and the gray wire, that quantum state is going to experience these gates in a superposition of both orders at the same time. And this is something that can't be described by the quantum circuit model. I do want to say that the quantum circuit model is universal, so you could simulate this scenario. But if you simulate this scenario, it turns out you're going to need an additional copy of one of these gates. So you would need at least, say, 2 copies of U1 and 1 copy of U2, and then you could simulate it so that the outputs of your now larger quantum circuit would mock up this these statistics. But given these limited resources, you cannot describe this with the quantum circuit. For the quantum switch, we want to go one step further. What we're going to do is we're actually going to add a second qubit, a control qubit. And that control qubit is going to coherently control the order in which now our target qubit psi is shared between the gates U1 and U2. So now we have a state of the control qubit. These gray things are some hypothetical controlled path gates. And essentially the idea is if the control qubit is in the state 0, then this qubit is going to take the black wire and go to U1, U2. So the output of the circuit will be U1 acting on psi followed by U2 acting on psi. However, if the control qubit is in the state 1, then we'll go through the gray wire. So the state psi is going to see the gates acting in the opposite order. And this is a quantum switch as it was proposed in the original paper from Kiribella. So this is interesting. It's something we can do that goes beyond the quantum circuit model, but is there any reason for doing this, or is it just some mathematical curiosity? Well, it turns out there are certain tasks that we can now do more efficiently using these types of scenarios. So the first task, which was proposed in this paper by Kiribella, and I think it's the simplest one to understand, so I'll present that one here, is the following scenario. So we're still going to consider our two gates U1 and U2, and now we imagine that there's a referee, and the referee tells us that the gates U1 and U2 either commute or they anti-commute. And your goal is to determine which of these two statements is true. However, you're only allowed to use each gate once. And as I kind of alluded to earlier, with a quantum circuit, this isn't possible. So with a quantum circuit, you can't deterministically win this game using each gate once. If you want to win the game deterministically, what you'll need to do is use one of these gates multiple times, and then you could accomplish this. However, if we now have the quantum switch, it's very easy to see that we can actually complete this task. So again, I showed you this was the operation of the quantum switch. So if the control qubit is in the state 0, we apply the gates in one order. If the control qubit is in the state 1, we apply the gates in the opposite order. So now, if we put the control qubit in a superposition, now we create this this following state here, which looks like an entangled state, where now what's entangled is, and I use the word entanglement somewhat loosely, but is the order of the gate application with the state of the control qubit. Of course, whether or not the state is actually entangled is going to depend on the precise form of U1 and U2. For example, if U1 and U2 are both identity, then this won't be an entangled state. But for certain choices of U1 and U2, you'll end up with an entangled state. So now all we're going to do is rewrite this state. So I'm just going to rewrite the control qubit in the plus minus basis. So just write 0 as 0 plus 1 and 1 as 1 minus 1, or and then factor, and we end up at with the following state. So now we have, if the control qubit is in the state plus, we have the anti-commutator of U1 and U2 acting on psi, whereas if the control qubit is in the state minus, we have the commutator between U1 and U2 acting on the state psi. So now all we need to do is measure the control qubit in the plus minus basis. If we measure the control qubit and we find that it's in the state plus, then we know that this term must be 0, even with a single use, because now we're making use of the referee's promise that the gates either commute or anti-commute. So if we find the control qubit in the state plus, we know for certain that the second term is 0, so the gates commute. However, if we find it in the state minus, we know that the gates must have anti-commuted. So this is already something that we can do with a quantum switch, which goes beyond the standard quantum circuit model. So we can do this task more resource efficiently than you could with a comparable circuit. And since then, there have been really many applications, and this is quite an incomplete list, actually. So I think this list only goes up to, I think, even the beginning of 2021. So there's now applications in a range of fields. So there's certain applications which are similar to the game that I presented you, these kind of quantum computation or quantum protocols. And, for example, this commutation anti-commutation game has been generalized to something called the Hadamard promise problem, which now scales to multiple parties. There are applications in quantum communication complexity, quantum metrology. Recently, there's actually been a lot of work in quantum thermodynamics showing that you can use these sorts of processes to cool systems more efficiently. And then also applications in quantum communication. And actually just, I think it was last week or the week before, there was a paper from a group in China, which I don't have a reference to, which showed how you could implement a generalized Deutsch algorithm using the quantum switch more efficiently. So there's really a variety of different applications for these sorts of processes. So this is all well and good, but how do we actually make these sorts of processes? So this is a schematic of the first experiment we implemented back in 2015 using single photon states. So I'll just walk you through it. It's actually a relatively straightforward experiment where we prepare single photons and we send our single photons into the experiment from this bottom mode. And then we're going to encode the target system in the polarization degree of freedom of that photon. So we have some polarization state psi entering the experiment. That photon then sees the beam splitter, and this puts the photon in a superposition of the transmitted mode and the reflected mode. And we can think about these spatial modes as encoding a second photon in a second qubit in the same photon. So if the photon is in this mode, we say that the control qubit is in the state 0. If it's in this mode, we say the control qubit is in the state 1. And now we can see what happens. if, once we've added the path qubit, we're now in a superposition. So the photon's in a superposition of this mode and this mode, or in the state plus. If in the branch of the superposition where the photon was transmitted, we're first going to experience these set of wave plates, which you can use to implement U1. The photon will then loop around to these set of wave plates, which implement U2. On the other hand, if it's reflected, the photon will first go to U2, then loop around, and then see U1. So in this way, we can already implement this superposition of these two operations acting on the polarization state of the photon in a superposition of two orders. And finally, at the end of the experiment, we can perform measurements on the path qubit. So you can use, by setting the relative phase and using a beam splitter to re-interfere the two path modes, we can implement the measurements of the path qubit in this superposition basis. And then we simply record whether the photon exits in this port or in this port. So this is nice, and it works quite well. In addition to our experiment, there are several other groups who have done these sorts of experiments, with sometimes with slight tweaks, but it's roughly the same idea. And what I want to point out is actually one experimental challenge in scaling up these sorts of processes. So in the previous interferometer I showed you, each order that we superimpose requires one path of the interferometer. So when we only have two gates, this is fine, because then we only really have two paths, because we can either apply the gates U1 before U2 or the other way around. So there are two relevant orders. However, for many of the applications, they require something called the straightforward generalization of the quantum switch is the N switch, or the N gate switch. And this has N factorial orders. So for example, if we have 3 gates, now we need to implement, we need to make a much larger interferometer with 6 paths, and then re-interfere all of those paths and perform measurements on that path degree of freedom. So it becomes an experimental challenge. For the 4-gate switch, it turns out we need 24 paths. And if you think about implementing this experimentally, in addition to building the interferometer, just fitting 24 paths through a single half wave plate already starts to become quite challenging. I want to point out at this point an experiment from a group in South America where they implemented a 4-party quantum switch. However, exactly because of this challenge, they were only able to implement 4 orders of the superposition. So that here their gates are done again on the polarization degree of freedom. So they have gates A, B, C, and D. And if you follow these paths through, essentially these are fibers connecting the photon from this gate, then out here into D, which is down here, and then to this gate, and then that goes to C, which is over here. And then in this way, you can implement the subset of orders. So this requires multi-core fibers. And again, it's a 4-mode interferometer, which needs to be phase stabilized. And this is experimentally challenging. So this is one of the reasons we decided in the last couple of years to move to a different architecture in hopes that scaling these sorts of processes up to multiple gates would be a little bit more feasible. So the workhorse of these experiments are ultra-fast optical switches. So now I apologize for the terminology. These are optical switches. These are classical devices, which we're now going to use to build a quantum switch. So there's kind of 2 levels of switches. When I write it, I try to write the optical switch in lowercase and quantum switch in uppercase. But these are our optical switches, and they work as follows. So they're 2x2 devices, meaning they have 2 input modes and 2 output modes. And we can put these switches in 2 states, what we call the bar state, where input 1 goes to output 1, and input 2 goes to output 2, or the cross state, where we then cross the modes. What's nice about these is these are commercially available devices. You can get them from many different telecom providers. These are some of the specifications of the switches, the particular switches which we use. But what's important is that they have a relatively high repetition rate, a high frequency of operation. So we can switch these things in a matter of tens of, or about 50 nanoseconds. So what this looks like is as follows. If we put a photodiode in each of these output modes and just measure the power, that's what, as a function of time, that's what's plotted here. So the yellow curve this is just an oscilloscope trace of the classical measurement where we're looking at the light in mode 1 and the light in mode 2. So these are just photodiode currents or voltages. And now we apply an electrical pulse. So we start out, we'll start here. We start out with most of the light coming out in mode 1 and essentially no light coming out in the yellow mode. And as soon as we apply the pulse, in about 50 nanoseconds, with about a 50 nanosecond response time, the switches alternate. So they go from bar to cross and we can flip the outputs. So now we want to use these optical switches to create a quantum switch. And the way we're going to do this is based on a theoretical proposal by Rambo in 2016, where we're going to create a network of optical switches to route the photon through these gates in a superposition of different orders. And in this theory paper, they talk about a precise architecture in which we can scale this up to multiple parties. And the nice thing is we only have one spatial mode traversing each optic. However, there is a cost. I'm just hiding the difficulty somewhere else, and I'll get to that a bit later. But just to show you how we do this experimentally, what we do is we start with a down conversion crystal. So we pump it and we generate photon pairs. So we have one photon coming down here and one photon coming up. We immediately detect one of the photons, which we use as a heralding photon, and it also sets a time reference for our experiment. So once we detect this photon, the experiment kind of starts. The second photon then goes to this imbalanced Mach-Zehnder interferometer with a long arm and a short arm. And then we choreograph the switch so that initially the optical switch is in the bar state, so that the photon, if the photon goes in the short mode, it's going to be transmitted. And then we immediately switch the optical switch based off of this detection event to the cross state, so that then the photon which went in the lower long path switches up to this mode. And in this way, we can put a single photon in a superposition of these two time bins. So now, rather than having two spatial modes, we have two time bins, and we have our photon either in this early time bin or in this late time bin, and we can create this state deterministically. Right, and we're now going to use this time bin degree of freedom as our control, as the control degree of freedom for our experiment. And I'll show you here how this works. So we start by generating our time bin qubit using the setup I just showed you, and that comes in from the left here towards our optical switches. So now we have two optical switches, and we have our two gates U1 and U2, and U1 and U2 are going to act on the polarization degree of freedom of that photon. So in our experiment, we actually start with the optical switches first in the cross state. And what this is going to do is it's going to send that first time bin down to U2. So now in this branch of the superposition, we pick up this U2 operation acting on the polarization degree of freedom, or the target degree of freedom. After this, we're immediately going to change the state of the switches into the bar state. That's then going to route the second time bin straight through the optical switch up to U1. So then we pick up this U1 in this branch of the superposition. At the same time, the first time bin to enter the experiment is going to see the bar state here, and it's going to enter this loop, and then it's going to propagate back from the right to the left this way. This fiber doesn't do any, we take a lot of care to ensure that fiber doesn't rotate the polarization, so it just implements identity, so we don't pick up any additional operations acting on the target degree of freedom. Then, as you might have guessed, we again change the state of the optical switches, now from bar to cross. This then routes that time bin 0, which was coming in this loop from below up to U1. And then we pick up this U1 operation acting in this branch of the superposition. At the same time, the time bin 1, which was up in this upper mode, goes down into this loop and is now propagating from right to left. We then switch or change the state of the switches one more time. And this routes the first time bin now out of the experiment, and the second time bin down to the state U2. And then what this does, so then at this point we have U2 acting in the second branch of the superposition. And then by changing the state of the quantum of the optical switches one last time, we have both time bins exiting in this path degree of freedom. So what this does now is it implements exactly the quantum switch operation that we wanted to. So we've created a superposition of the gates acting on the photon in both orders, where now we've used the time degree of freedom as the control. And again, the nice thing is we have only a single spatial mode traversing each optic. However, we now need to have multiple time bin modes traversing each optic. So it's really a question of which is ultimately going to be easier to scale up. But the nice thing is, if we were to make a larger network where we have multiple gates and multiple switches, we then have a lot of flexibility, because just by playing with the optical switches, we can tune exactly which operations we implement in which order. We could in fact keep the photon in the loop longer and apply U1, U2, U1 if we wanted to, even in the experiment we already have built.
Can I ask you a question here?
Yeah, of course.
So going back at this time bin thing, is it, how should I interpret it? And I know that you cannot go to the rest frame of a photon, but imagine that you could go to the rest frame of the photon. Then I would see a single photon wave function which has two spatial peaks separated by a distance d. Yep. That's what it is.
Yeah. So if you think about that, there will be experimentally we think of this between both in terms of time and in terms of space, because we have to make sure that our optical fibers are long enough between the photons. So we do imagine actually that if you freeze time, say, you'll have a pulse at an earlier time and then some distance separating the second pulse. But it's one photon in a superposition of both of these pulses.
Right. Okay. So So in if there was a rest frame, I would just think this is like a single wave function with two very distinct peak, with the probability in between practically going to 0.
Yes. Yeah.
Okay. Thank you. That's very interesting.
Yeah. Right. So this is the idea. And as I said, there's a way of scaling this up to multiple parties, but currently we have the 2-party version, or the 2-gate version, built in the lab. This is a schematic of the entire experiment. The details aren't too important, but in the green section here, we have the quantum switch I just showed you, made up of 2 optical switches in our 2 parties. Here they're labeled Alice and Bob instead of U1 and U2. Up here in the yellow section, so sorry, I should actually start in the right order. We have our photon source over here, which makes photon pairs. One of those photons is immediately sent to a detector. The second photon comes up into this yellow section. And here we have our imbalance interferometer made up of a fiber delay and a shorter fiber. We have an optical switch, so we can deterministically make our time bin qubit. So this superposition of these 2. This fiber then propagates down here through this orange section where we can prepare the state and the polarization state of the photon. And then this loops around all the way down here into the quantum switch. And this is the setup I just showed you on the previous slide. After the quantum switch, the photon comes up into this path, and actually, this is one reason why we like this experiment as well, is now the photon is coming back this way, and we reuse the same interferometer to perform measurements on the time bin degree of freedom. I don't have time to get into the precise details of how we do this measurement, But we use the same interferometer, and by adjusting the phase and the settings on the quantum switch, we can measure this time bin qubit in different bases. And the other nice side effect of this is we're using the same interferometer to perform measurements as we are to prepare the state. And it turns out this leads to a passively stable experiment. So any phase fluctuations completely cancel out. So we can have extremely long acquisition times, and this wasn't the case in most previous experiments. So we have this built, and it works. So what I'm showing here is the results of playing this commuting anti-commuting game with our setup. So here is the probability to find, so along the y-axis, we have the probability to find the photon. Sorry, this should be labeled port plus and port minus in the notation. So in the notation I'm using here. So if it's green, then we find the photon in the state plus. If it's blue, we find the photon in the state minus. And on the x-axis, I'm labeling which unitaries we have implemented in place of the switch. So for U1 and U2, or Alice and Bob here. So when the two gates are identity, we find the photon almost always exits in this in one port, corresponding to finding the control qubit in the state plus. This is the same when it's identity X, identity Y, identity Z, X identity, and XX, as it should be, because all of these gates commute. However, when we implement XY, these are two poly operators, and the different poly operators anti-commute. So now X and Y anti-commute, and we then find the control qubit to be in the other state. And this is consistent for all of the poly operations. And in addition to this, we verified it for other sets of gates. So this works. But now we actually wanted to go a step further. And since we have this passively stable architecture, we decided we wanted to perform full process tomography on the switch, because now we can deal with very long acquisition times. So we've done this, and this is detailed in this paper that I mentioned earlier, which just came out on the archive this morning, Higher Order Process Tomography of a Passively Stable Quantum Switch. And I'm not going to get into the details of the process tomography, but I do want to mention that we actually had to develop a new theory to do process tomography on the switch. And the reason is as follows: is you imagine the switch, if you want to write it in some quantum circuit-like picture, you can imagine some box which implements a quantum switch, and we have a control qubit and a target qubit. So this is a 2-qubit process. However, standard 2-qubit process tomography doesn't access the underlying causal structure that we're trying to get at. One way of seeing this is that the precise reconstruction that we would get if we did process tomography depends on the operations we implement. So on the precise settings of U1 and U2. So if these are both identity, then it turns out the whole 2 switch will also be identity. However, if they're anti-commuting gates, then we have different behavior. And in general, we're not required to make U1 and U2 commute or anti-commute. They could be an arbitrary gate with an arbitrary commutation relation, and then we would have a different process. So the process that we reconstruct depends on the states U1 and U2. And what we want to get at is some different representation which abstracts out U1 and U2 and treats U1 and U2 as inputs. So in this way, if you imagine this shaded W area representing the quantum switch, normal process tomography, we would vary the input states, so send in a complete set of input states and perform a complete set of measurements at the output of the quantum switch. However, now to build the quantum switch, or to characterize the quantum switch, we also need to treat Alice and Bob's operations as inputs. So we now need to implement a complete set of operations on Alice and Bob's space. And this is complicated. It turns out unitary operations don't actually suffice. In general, we have to do non-unitary operations to do complete process tomography. So in general, this is required for the quantum switch, but there's also a field of quantum information theory which studies higher order quantum transformations. And these higher order transformations are exactly this. There's some quantum process that takes as inputs not only quantum states, but also quantum processes. So we had to use some of the tools from this higher order, the theory of higher order quantum processes, to develop a new protocol for doing process tomography on the quantum switch. Again, I'm not going to go into the precise details, but we perform process tomography and it works. I do want to stress that our experimental implementation being passively stable really helped. We needed on the order of 10,000 different measurement settings, and this took about 36 hours of continuous data acquisition. So it was really important that we had a stable phase throughout the experiment. So before I move on, I also want to mention that these processes are, aside from just applications, these processes are interesting for foundational reasons. And I think one of the nicest ways to see this is via this paper by Czesław Bruckner, Fabio Costa, and Ognian Oreshkov, Quantum Correlations with No Causal Order. And the reason that these guys are interested in these sorts of processes is that if you think about events in our everyday experience, these events follow a definite fixed order, just like the gates in our quantum circuit. In a way, you know, you never experience a superposition of different orders in your everyday life. So we can also associate an event with the application of each of our quantum gates, and then we can draw a space-time diagram of this event or of this situation where we have gate U1 and U2, and then we have the photon traversing U2 and U1. And now if we put the photon in a superposition with a sufficiently long wave packet, it's genuinely impossible to tell if the photon experienced this order or this order. It really experienced these events in different orders. And one of the consequences of this was is the following simple game, which was proposed in this NatCom paper I just pointed out. And the game is quite simple, so I just like to quickly walk you through it. We imagine a two-party game. We have Alice and Bob. These are going to be the inputs to the quantum switch, or but these Alice and Bob are given the following task. So each of them is going to flip a coin, and at the same time they flip their coin, they have to guess the result of the other party's coin flip. So this means, and then after this, the referee is either going to randomly ask Alice to guess the result of Bob's coin flip, or Bob to guess the result of Alice's coin flip. And now it's important that for the argument that they actually generate their guess at the same time they flip their coin. Because now what we're going to do is we're going to assume that Alice and Bob want to work together and they want to win this game as much as possible. And if we imagine that the processes must proceed in a fixed order, there's a very simple strategy which is optimal. In this case, say Alice acts before Bob. So if Alice flips her coin and she gets heads, then she can just send Bob the result of her coin flip. So she can just say, Bob, I got heads. Now Bob is going to flip his coin, and then he's also going to guess Alice's coin flip. But now he knows that she got heads because she just told him. However, when Alice flipped her coin, she also had to output a guess of Bob's coin flip. But Bob hadn't flipped his coin yet. So the best she can do is randomly guess. And in this case, if the referee asks Bob to guess Alice's coin flip, Bob will be able to guess it perfectly because he knows, because Alice has told him. However, when the referee asks Alice to output the result of Bob's coin flip, the best she can do is randomly guess. So in this case, the success probability is going to be 75%. So when the referee asks Alice, she'll get it. She'll get it right 50% of the time. When she asks Bob, then Bob will get it right every time. However, it turns out that these sorts of processes, not the quantum switch specifically, but processes like the quantum switch can actually violate this inequality. So in this paper, this NatCom paper, they presented a particular quantum process which can win this game with, I think, 86% of the time. So in this game, it's really impossible to ascribe a fixed order of events between Alice and Bob. So this has led to the notion of processes which are either causally separable or causally non-separable. And although the quantum switch can't win this game, it turns out it is a causally non-separable process. I'm just going to more or less leave it at that, but I'm happy to discuss this later in the question period. We've also done some experiments where we've verified the causal non-separability of our experiments in different ways. And yeah, and I think these are interesting topics experimentally to see what sort of processes we can actually implement and what implications they might have on on these, this idea of really indefinite causal order. Okay, so with this, I think I have, how much time do I have left? About 15 minutes or so?
Yeah, surely.
Yeah, okay. Then I'm going to switch to something completely different. So if I've lost you, then now's your chance to pay attention again so I can lose you again. But what I'd like to talk about now is an experiment which came out last year where we implemented Maxwell's daemon with correlated baths. So, so before I get into our experiment, I just want to briefly remind you of this idea of Maxwell's daemon, where we have the following thought experiment. We have two boxes containing a gas, which gas is at initially at thermal equilibrium, and the daemon is going to monitor the velocity of each individual particle. If he sees a hot particle coming, a fast-moving particle coming towards the door from the left, he's going to open the door so that the fast particles end up here. And if he sees a slow particle coming at it, then he's going to open the door so the slow particle goes over here. And doing this, he can end up with a situation where all the slow particles are on this side and all the fast particles are over here. So he can create a temperature gradient and then use this to extract work. So the reason, so in the modern language, what we're saying is the daemon is essentially doing something called measurement and feed forward. He's measuring the state of these individual particles, and then he's applying some operation on the global state based on the result of this measurement. So this is the idea. We do a measurement, then we feed forward that measurement result to change the state of the system. And now what I'd like to show you is how we can implement this idea using quantum photonics. So this work is based on this experimental paper from Ian Walmsley's group back in 2016, where they both proposed they presented the first proposal of the photonics Maxwell daemon together with an experimental implementation of it. So the basic idea there is, rather than considering two boxes containing a gas, we're going to consider two thermal states of light. So in this case, the thermal state of light is, we have one thermal state of light in this mode and one thermal state of light in this mode. And in a thermal state of light, I just want to remind you that the temperature of that thermal state is proportional to the photon number. So the more photons in the mode, the hotter the temperature. And then what the daemon is going to do is, so then what we're going to do is we're going to start with two thermal states with equal photon number or equal temperature, and then the daemon is going to perform some measurements on that state to attempt to create a photon number imbalance to create this temperature gradient, which we can then use to extract work. So more precisely, what the daemon is going to do is use photon subtraction to measure the temperature of the mode. So what that looks like is actually fairly straightforward. It's just a beam splitter and a single photon detector. So now, although the temperature of each of these thermal states is equal, when I say this, it's of course equal on average. The thermal state of light has an indefinite photon number. So, shot by shot or instantaneously, the photon number is going to fluctuate in each of these beams. And now, if say the daemon sees a photon hit this detector, he's quite sure that the temperature of this thermal state is instantaneously higher than the temperature of this thermal state. And now he's going to use feed forward based on this information in order to create this photon number imbalance. So in the first experiment by the Walmsley group, they didn't implement the feed forward operation. They rather observed the effect in post-processing. But they had this nice schematic, this nice setup where the two thermal states were incident on photodiodes, and then they connected it in a fairly simple circuit where they could then ideally use this circuit to charge a capacitor. So the work would then be extracted by charging this capacitor. So if both the photon number in each of these beams is equal, then these two photocurrents essentially cancel off, so there's no net charge across the capacitor. And then what they did is they measured the voltage across the capacitor in real time and correlated it with detection events at the single photon detectors, and were able to verify that when this detector clicked, indeed there was a slight negative voltage on the capacitor, and when this detector clicked, there was a slight positive voltage on the capacitor. So our idea was then to use our 2x2 switches to actually implement the feed forward. And that's done so we did that using, again, a very similar setup to what I just showed you. However, before the two detectors, we now place one of our ultra-fast optical switches. And then the idea is very simple. When the demon sees a detector in one mode, he now knows the temperature is instantaneously higher in this mode. So then in the case where we want to increase the temperature in the upper mode, the demon will do nothing. However, if he sees a photon down here, then he's going to know that the temperature is higher in the lower mode. So he's going to flip the state of the optical switch from the bar state to the cross state, and then route the hotter photons up and the colder photon bunch down. And then what we do is we don't, in our experiment, we didn't actually implement the circuit. We instead just recorded the photon number clicks here. And we observed this already on the singles count rate. So we weren't looking at any correlated events, but really just looking at the singles rates here and here, we were able to see the demon effect. So again, the goal, start with an equal photon number imbalance, and then generate a photon number imbalance by using our feed forward technique. And what's plotted here are the results of our experiment. So this is the photon number imbalance on the y-axis, normalized by the coherence time for technical reasons. And then what we're doing is we're actually increasing the reflectivity of the demon's beam splitters. So these beam splitters, the way we implemented it, we did it such that we had variable reflectivity, and we could tune the reflectivity from 0 to 50%. And we see that when the reflectivity is 0, we're generating essentially no photon number imbalance. However, as we increase the reflectivity, we start to see that we can generate more of a photon number imbalance. And the reason you can think of this is this effect. You can think of this effect working as follows. When we increase the reflectivity, we're giving the demon more information, so we can use that information to extract more work or to generate a larger photon number imbalance. However, we wanted to go even further. Since the demon is using information to generate this imbalance or to generate this work, what we now wanted to do is give the demon more information. And one way you can think about doing this is by using correlations. So now we again go back to this gas box picture. If when the demon detects a photon in the right-handed box, if we could create a state where for every photon in the right-handed box moving towards the door, there's also a photon moving, or there's also a particle in the other box moving towards the door, and we learn what its temperature is, then the demon is gaining information about more particles, and he can use this to adjust his feed forward protocol to generate a larger photon number imbalance. Of course, this is almost impossible to do if we're using massive particles, but with photons, we can create these sorts of correlated states fairly easily. In particular, if we use down conversion, then we create a state where for every photon in mode B, there's a corresponding photon in mode A. And then we can do this for all photon terms. So if there's 2 photons in mode A, there are 2 photons in mode B, and so on. The nice thing about this state for our current purposes is if you trace out one of these modes, each state on its own is left in a thermal state. So now we have 2 thermal states in our modes A and B, but we have these correlations. So now, right, so now when the daemon sees a photon up here, he also learns something about the photon number down here. And then he can adjust our feed-forward protocol to take advantage of this. So with down conversion, it turns out that this works, and it works quite well. So what's plotted here is, again, the photon number imbalance versus the reflectivity. We set the experiment up so that we had the same average photon number in both cases at the beginning. And we see that for the uncorrelated baths, we were able to generate some photon number imbalance, but for the correlated baths, we can generate a much larger photon number imbalance. However, it turns out this only works in the low temperature limit for correlated baths, because the daemon, the effects actually work opposite to each other. So when the daemon, so for this down converted state, when the daemon detects one photon up here, it learns that there's also a photon down here. But because this is a thermal state, when he detects a photon up here, he also knows that there are momentarily more photons in this mode because of the photon subtraction result, the thermal effect that I presented to you initially. So in this case, these two effects work in the opposite direction. So then the question is, can we create a correlated state to which should also work for higher temperatures? And you can do this by creating a superposition of these so-called noon states, where now for every photon, when we see n photons in mode A, we know that there are 0 photons in mode B, and vice versa. When there are n photons in mode B, there are 0 photons in mode A. In this case, when the daemon detects a photon, say 1 photon up here, he knows there's another photon down here, and this is in the same mode where we're going to have the thermal effect. And in this theoretical proposal, it was shown that you can actually tune these alpha coefficients to create states such that when you trace out each mode, you are left with a thermal state. So then you have kind of everything you need. So we implemented this experimentally. So these are the green data I showed you before for correlated baths. This is the red data for the uncorrelated baths. And in the low temperature limit, everything works. And the anti-correlated data are these blue results, which actually perform slightly worse for low temperatures, but this is because we had to use Hongo-Mandel interference to generate our state. But we expect, as we tune to higher temperatures, that the anti-correlated states will actually start to outperform the correlated states. So with that, I reached the end of what I wanted to cover today. I showed you, I started out by showing you the quantum switch, discussing applications and its relation to foundational physics. And then I focused mainly on our new results on our timed-in quantum switch, which may be more easy to scale up to multiple parties. However, it comes with its own technical challenges. And finally, we discussed this Maxwell daemon, which I think is a nice, which is a nice result in that it shows that we can implement some of these thermodynamic ideas also in a quantum or also in a photonic setting, and it gives us kind of a new handle on these systems. So the types of correlated states that we implemented here would be very, very difficult to implement using massive particles. Of course, there are other things where we would struggle to implement in photonics. So I think it gives us the opportunity to study a different type of thermodynamic problem using quantum photonics. So with that, I'd like to thank you for your attention, and I'm happy to take any questions.
Thank you very much for the very intriguing talk. I mean, it was indeed very interesting. So any questions from the audience? Please unmute yourself and ask. Any questions?
I have 2 questions. Can I ask?
Yeah, please go ahead.
Thank you for your talk. The first question is, in your presentation, you are using actively or heavily optical elements. So that may bring vacuum noise, scattering, absorption of photons. So the question is, did you consider or plan to consider such mechanisms in your calculations, or maybe they are not significant?
Yeah, so for most of them cancel off in a way, because the loss is more or less equal to every mode, but the loss and the scattering off of these optics is actually one of the main challenges for scaling up to multiple parties. The loss just gets worse as you add more of these optical switches around. So from the point of view of the quantum switch, I think it's a fairly straightforward interpretation. It's just an overall loss. But once the photon gets out, then it has this, then it has experienced an indefinite causal order. In some of these works I cite down here, experimental entanglement of a temporal order, for example, there we were trying to verify that the order was really indefinite without making any assumptions. And we did this by trying to do a device-independent study, by doing something like a Bell violation. And because of the loss in our experiment, we weren't able to do a loophole-free Bell test. So if you want to do these sorts of device-independent or theory-independent verification, then the loss becomes important for these sorts of reasons. But we're kind of, I'd say the field is kind of at the state where we're, developing techniques, and currently a lot of effort is going to writing or to try to use established device-independent techniques to address these issues. And loss will come in very heavily when you start really trying to close the loopholes. So right now we have these loopholes in the detection efficiency, but we're kind of saving it for future work. Yeah.
Second question. In one of your slides, you mentioned application of quantum switch. So yeah. My question is, what kind of benefits one can expect in quantum metrology by using quantum switch? So maybe.
Yeah. So there's one result which shows, from what I recall, getting I think there's kind of two ways of going about it. So one line of work is focused on going to like a Heisenberg scaling with number of uses of the unknown unitary. So people are typically talking about, well, actually there's been work both on multi-parameter and single parameter metrology. But it's really, so there's work trying to go into like Heisenberg scaling. And the other idea is to do quantum metrology in the presence of noise. So if you imagine you're trying to estimate some noisy quantum process, then it turns out because of the commuting and anti-commuting behavior of the quantum switch, the fact that it kind of separates out the commuting noise, the commuting part of the channel from the anti-commuting part of the channel. So everything that exits in one port of the interferometer has the stuff that commuted, and the other port is the stuff that anti-commuted. So now if your channel is noisy, then depending on your noise model, a lot, you can think about a Krauss representation, for example. So if a lot of your Krauss operators commute, and the noise comes from the commuting Krauss operators, then you kind of post-select on the anti-commuting channel. And then in that channel, you have less noise. So it depends specifically on the noise model. But I'd say those are the two directions people are going with respect to quantum metrology.
Thank you.
Any other questions? If not, maybe I have a quick question. You did talked about the Maxwell domain and this possibility of separating out particles in terms of their kinetic energy. Is it possible to do similar things with spins, that you separate out up spins and down spins on the two sides? And in this case, I'm thinking of electrons, but with photons, probably with polarization degree of freedom. Is this a possibility, or?
We've thought about it. I think because we've thought about, like, say, using a Bell state to actually take advantage of some entanglement, but we didn't have any. We weren't able to come up with a real advantage, let's say. So
Mhm.
because I also want to point out that actually we weren't really using entanglement. So we just had correlations. We were just measuring in the computational basis. So we didn't really require entanglement. But it's to use, like, for us, polarization, it's definitely an option. You might have to think about the analogy to Maxwell's demon again, but we just weren't able to come up with a protocol that worked better, but we didn't have any proof that it couldn't be done.
I see. Because in electrons, it's more like developing magnetization or something which
Yeah.
could be of interest. So
Yeah.
that's why I'm kind of curious about it. And also in the first part of your talk, you talked about, I think it's more like saying that if you have interferometers built into the circuits, then you have something new, right? You essentially have interference. U1s and U2s are more like an interferometer.
Yeah.
Something like a Mach-Zehnder interferometer being introduced, right? It's a one-way interferometer.
Yeah.
It doesn't go back and forth, but it goes one way and interferes. So I'm curious if this has connection to some kind of topological quantum computation, where essentially all the operations are through interferometry kind of approach.
Yeah, it's a very interesting question, but I don't know. I haven't seen any results in the field on that. Yeah, so I don't think I can really comment on that.
Because in
But-
many cases, the gate operations are essentially, implemented through braiding operations. So imagine that you have the braiding operations being the gate operations. In that case, of course, you will need something like an interferometer to implement your gates.
Yeah.
It's natural to the system. And then I wonder, won't though they automatically kind of run into such problems, or they don't? And it's just a curiosity.
Yeah. Yeah, I'm really not sure. I'm wondering if maybe there's relation to some of this noise cancellation ideas, where you can get some of the noise resistance from topological computing. But no, I don't know. I don't know if it's exactly the same, because you're in the noise cancellation works I've seen, you're typically always post-selecting, and in topological quantum computing, you're just making something that's kind of, I guess, intrinsically stable.
Yeah, but okay. So the thing which I had in mind is that usually the operation, the unitary operations which you want to implement, they are done by having some localized quasi-particles in the bulk, and then you have an interferometer around it, which have another quasi-particle going around it, such that you exchange them. Like one moving guy and there's one static guy sitting in the center, and typically implemented via interferometry.
Yeah.
So I wonder, like this is something which will automatically come there. It cannot be helped, because that is how the gate operations are implemented.
Yeah. Yeah, I mean, it might be interesting to look at the topological model and see if you can write it in terms of an indefinite causal order. But yeah, I really don't know.
Okay. That's okay. Thanks a lot. But anyway, thank you very much for the very interesting talk. So I hope we see you sometime physically here.
Yes, that would be great.
Yeah. See you then. We move on. Thank you.
Thank you.
So the next Delhi Technical University, and he will